So machine learning is a very interesting topic in today's research. It offers a lot of advantages to the toolboxes of researchers. However, it comes with its own interpretability and transparency issues. So welcome to my presentation, Improving the Understanding of Machine Learning Predictions Through Maps, which I submitted to the MSc Cartography program in 2024. So in this presentation, I'll walk you through the motivation and problem, objectives and research questions, methodology, results, discussion, and finally the conclusion. So there are complexities in real-world data today, and that is why researchers are employing a lot of complex black box models to be able to understand these complexities. Now, these models are returning what I call non-transparent maps because in the end, the users who are supposed to consume these results do not understand how certain predictions were made. Now, as a result, the European Union has also set up the artificial intelligence law in 2024 to be able to curb some of these problems. And then I aimed my research on the local interpretability of a black box model. And here I'm looking at how cartography can also support the visualization of the local interpretability. And I'm looking at random forest model. So regarding the objectives, I looked into literature to understand what local interpretability models exist and which ones are effective. And secondly, I proposed a workflow as to implementing the most effective local interpretability model. And finally, I implemented this workflow by looking at the technical steps and challenges involved, as well as engaging users to understand their perspectives. So basically, regarding the literature review, I assembled these local interpretability models, and I finally selected the SHARP model due to its level of adoption and then also the strong mathematical background. Then secondly, this is the workflow that I designed. And here, for example, is where I am doing the local interpretability model calculation. And on the right-hand side is where I am creating the maps. So thirdly, regarding the implementation, on the left-hand side is the study area where I selected a case study in digital soil mapping. So here, the yellow dots are indicating where soil total nitrogen were sampled, and then the black dots are where I am doing the predictions. And on the right-hand side are the sources of data where I am extracting data from Google Earth Engine. So regarding the results, my map is what is shown in the middle compared to maps from external sources. And here we see that there's a general pattern. For example, the northern part of the study area is having low soil nitrogen levels compared to the southern part of the study area. Now, the interesting part of this research is the SHARP results, which is the local impacts of these predictors. So on the right-hand side is a summary plot, which is telling us the hierarchy of how these predictors behind the model are influencing the prediction. So the one at the top, for example, is the most influential predictor. And here, cartography is helping us to see, for example, the blue areas are where this predictor is making decrements to the predictions, and the red areas are where it is making increments to the predictions. The map on the left-hand side is just the raw map for the variable. The same thing applies to this second map and then the third map as well. Now, we can put all this information together to create what we call the local predominant predictor map. So here, this map is telling us that for every pixel, what is the highest or the most influential predictor at that location. And so we see that precipitation of driest quarter, which is the gray color, is controlling a lot of areas at the northern part of the study area. However, we also see red and yellow areas being controlled by temperature. Now, regarding the user survey, I had 102 respondents, and in terms of the analysis, I am using the max median score. So on a 5-point Likert scale, we can see that readability is achieving a high score of 4, interpretability is also achieving a high score of 4, and understanding is achieving an average score of 3. Now, this could be as a result of the low domain knowledge respondents within the survey. Now, regarding the discussion, I had some limitations. For example, I couldn't visualize more than 7 variables in one map, and also there were few soil domain knowledge respondents. Computations were very high regarding the SHARP computations, as well as the huge size of data that I was doing the predictions for, but I was able to overcome them. And here I am recommending for future work to consider geovisualization techniques to be able to overcome visualizing only 7 colors in one map, and then also consider color impaired users, looking at what kind of colors to select for the map. And also future work should consider in terms of the domain knowledge users. I mean, they should include more domain knowledge users in the user survey and also use high performance computers for big data. Another interesting aspect is to consider quarterly time series instead of monthly time series to be able to overcome multicollinearity, which is something I encountered in my research. So regarding the conclusion, I'm saying that the SHARP model is able to support local explanation of the machine learning models as we've seen in the results. And then the proposed workflow that I designed is also adaptable to a use case, for example, digital soil mapping, and also implementable. And finally, cartography, as we've seen with the maps, are able to enhance readability and interpretability of the results. And it also helped us to understand that temperature and precipitation are the driving factors of soil total nitrogen in Burkina Faso. So thank you very much for your attention. And once again, my name is Isaac Newton Kisiedu. Bye.